Okay, so today we have yet another really exciting lecture about essentially this lecture covers what's inside the program. Or in other words, we can say that the lecture is about how the programs get compiled and linked together. And we will spend 2 lectures on this topic, right? So we'll start today with kind of going slowly, introducing linking and loading. And then next time we will touch on position independent code and essentially how stuff gets loaded in Linux, right? So it's not about, it's about both x86, but it's also very much about Linux as well, right? So this is how programs are linked and loaded on Linux. And I will show you some examples as usual. Okay, so let's get started then. So what do you think is there inside the program if I ask you a question? So what shall be there? What parts of the program you guys know already? Any takers? Main? Yeah, so main. What is main? So it's part of which section? Remember, we talk a little bit about, oh yeah, cool, Shane. I'm proud of you. Data, BSS, and text, right? Shane knows. Okay, so look, yeah, exactly. So there is a data section, and data section is there to keep, remember, global variables, right? And data section can be roughly split into a couple of sections, so, right? There is data typically keeps initialized local, like global variables, meaning that if you have an int a and it's equals to something like 5, it will be placed, there will be space allocated for a, and 5 will be placed there. And that section obviously will be kept on disk, right? Because when you start a program, you really need to get this 5 from somewhere, right? So it comes from disk. But if you just have something like int a equals to 0, right? Well, let's say B, because we already used A. Then will be another section, which is called BSS, or in other words, it's called better safe space. Essentially, this section is not kept on disk, right? But it just like in the header file of the, in the header of the L file, there will be a size information about this BSX section, because you know that all the variables, all the global variables, which are not initialized, meaning that they will be initialized to 0, they will be kept in this BSS section. And it doesn't make sense to keep zeros on disk, because we know that they are zeros. You just can say, okay, let's allocate, for example, 4 kilobytes of zeros and just mem set them to zeros, right? Does equals to 0 count as uninitialized? Yes. So I should be more specific. It's all the variables which default to 0, right, and initialize to zeros. But I think it's initialized to 0, but it will go into BSS. We can double check if we want at some point. Okay, so we have data and have BSS. And I mean, like, that's a great question. So to be technically speaking, I'm pretty sure that compilers can kind of, you can put everything into data, right? You don't really have to, you don't really need to have a BSS, just, and you can link in such a manner that BSS is copied into data, right? So you can do different things, but I don't think it's common. So in most cases, BSS is just keeps the variables initialized to zeros or uninitialized variables. So these 2 parts we know. The other part inside the program will be the actual code of this program, right? Which is, for whatever reason, historically is called text, right? So this is the code of the program, right? This guy also will be kept on disk, right? So because we have to load it, right? And the 2 other parts, which we talked about, are the heap, right? For keeping dynamic variables, and stack, right? For keeping local variables, local variables, and also like implement function invocations, register spill, so everything what we covered in calling conventions, right? Okay, cool. So you knew it, and that's a slide which essentially enumerates what I just said. And roughly speaking, remember I said again, global variables are split into initialized, which go in data section, and uninitialized, which go into BSS. And BSS stands for better safe space, or there is yet more, another one more canonical name, and I don't remember it, so we can look it up. Local variables on a stack, dynamic variables are on a heap, right? And okay, and if we take a look at the address space of the program, right? So that's yet another representation, just very similar to the one which I just shown on the screen. So here we have address 0 here, and since it's a 2 to the 32 address space, so it's a 32-bit address space, right? So the max is 4 gigabytes. That's how many bytes you can address with 2 to the power 32 bits, with 32 bits, right? And that's a realistic layout of programming memory. So when I say realistic, it's not something what Linux uses today, and it's not exactly what x86 is using, but it's the layout which was used in the past by various operating systems, and it totally makes sense. And like by understanding this layout, you can just first understand what Linux is doing, and then you can understand what x86 is doing, right? So when we will have a lecture on exec, and if you remember, exec takes a program from disk, kind of something like bin WC, and it loads it in memory. So which means that it will have to take those sections from disk and like lower them in memory like this, right? And you, as a designer of the operating system, you can change this layout. You can decide what it will be, right? And linking and loading will just explain you what needs to happen to the program in order for it to run correctly. So this is kind of the topic of today. And let me just touch on this a little bit more soon. So don't worry if you don't understand everything. So again, here is a process text or code, data. So our global variables, right? We have heap above that data. So here I don't differentiate between data and BSS, right? So heap is growing this way. And who can tell me which system call can grow the heap? SBRK, yeah, good job. So do you know what happens when you do malloc? Because normally you never invoke SBRK, right? You always invoke malloc, and you say, look, malloc allocate me 17 bytes, right? And you say, well, this is a pointer. So who can tell me what happens inside malloc? It's just also kind of important to understand. Let me tell you. So malloc is a library, right? So the code of malloc will live in your, yeah, correct, sure, yeah. So malloc is a library. It will leave you, if you compile everything together, it will live in the same code section as the rest of your program, right? If you don't use dynamic libraries, which we're gonna cover later today or next time. But essentially malloc maintains metadata about the heap. So essentially it might say, look, I have regions which will have 3 elements of a specific size. So maybe this is for the size, let's say 8 byte, and this is for the size 16 byte, and this is for the size 32 bytes, right? And when you allocate 17, you're between 16 and 32, so you have to go and allocate actually a chunk of memory which is larger and the next power of 2. And metadata says, okay, those regions are occupied, but I found a non-occupied region, and essentially this is the pointer which you will get back. And if suddenly all these regions are already occupied, right, in this example, right, you say, look, I want to do malloc again. So there is another like P2, and you do malloc again, and you say inside malloc, you say, look, this area is completely full. There is nothing to allocate because the last one was allocated for this P1, right? So inside malloc, you say SBRK, and you grow a little bit of a heap. And on this heap, you will essentially like, again, allocate more of these data structures. Maybe there will be some kind of a linked list, right, which maintains the next open region, right? And then you, on top of this, you say, look, I got it. So this is the next empty region, and this P1 will come from here, right? So this is how like roughly malloc works, and it works on real operating system in a similar manner, besides the fact that people are trying to aggressively optimize performance of malloc, so meaning that allocation and deallocation is extremely fast, and you try to to make it like performant in face of multiple threads of execution, which run on multiple cores of the CPU, right? So all these concerns will essentially influence your malloc design, right? So, but roughly speaking, this is it, right? And another thing which I wanted to mention, like you can allocate stack on the very top of the address space, then heap and stack will be growing in the opposite direction, and might meet dynamically at some point. And at this point, you might say, look, I ran out of space. This is also convenient because if you try to allocate more space on the stack and the operating system catches a patch fault, it can dynamically grow the stack, right? Of course, this idealistic layout kind of falls apart in light of multiple threads because each thread will need a stack of execution, right? So you will really it will not be just one heap and one thread and one stack. It will be one heap and stack per thread, right? So which means that you will have to make compromises and say, look, I will allocate maybe 64 kilobyte stack for one thread and 64 kilobyte stack for another thread, right? So and of course you say again, another breakage of this kind of idealistic picture is that you say, if I want to support some kind of dynamically loaded libraries, I have to find region of virtual memory in which I will load them, right? So library will have its own text section and it will have its own data section. It doesn't need to have a stack because threads are active and libraries are passive, meaning that by default, when you load the library, it's just like symbols, global variables and data, right? So you don't need, and then if you later library itself, code of the library, create a thread of execution, then at this point, you will create another thread, another stack for this T3, for example, because maybe this is T1 and this is T2, right? Thread number 1 and thread number 2, right? So this layout of the address space in reality is slightly different, but it's still, again, as long as you understand what you need to run a thread, you'll be good. And another thing which I wanted to mention before I go away from this slide is that the operating system kernel is typically mapped in the top half of the address space. x86 uses a strict split, right? So it's 2 gigabytes for user and 2 gigabytes for kernel. There is a specific reason for that. Linux is using a different split on 32-bit machines. It's like user has 3 GBs and kernel will only have this 1 GB, right? But the idea is that the kernel is always here. So there will be text section of the kernel and a data section of the kernel as well. And there will be some stacks, and you will understand later on in the class which stacks are those, right? Each process will have a kernel stack on which it will execute. But the reason for this mapping is to essentially accelerate performance of system calls, because, and again, we will cover it later, but if you do an interrupt, you will immediately land on the interrupt handler in the kernel and start executing in the kernel, right? So you don't really have to change the address space, reload the page tables, right? So again, it's a little bit like future looking. So don't bother if you don't immediately understand what happens with the kernel here. It's just a heads up that this yellow part is mapped in the same address space, right? And I think many of you seen it in various blog posts online and various resources which discuss it, but by the end of this class, again, I guarantee that it will be very, very concrete. You will understand why it's done and how it's done. Okay, let me stop here for a sec, and I will take any questions.
Is the kernel address space mapped in the virtual address space of the process, or is it something different?
Correct. The entire diagram is a virtual address space of a process, right? Which starts from 0, goes to 4 GBs. And if you have another process, it will have a different address space with a slightly different text section, slightly different data section, of course, its own heap and its own stack, but the kernel will be the same. So this part will be identical because it's the same physical memory, which is mapped just multiple times in different processes. So this is P1 and this is P2. That's a good question.
No, one more question. So if it's in the same process virtual space, can a process directly execute the access the kernel memory address?
Okay,
like how would they?
Yeah,
How would they know? How would they
that's a
filter?
great question. And again, I guarantee that you will, by the end of this class, you will have a very concrete answer. And if you will not have it, I will ask it, so you will have it anyway. The reason is that this green part, the mechanism which maps the kernel is called page tables. And page tables will have a specific bit set, meaning that there's the notion of privilege level, kind of like ring 3, in which user is executing, ring 2 and ring 1, which are currently not used by modern operating system. And there is the ring 0, right? And the kernel is running inside ring 0. And this bit essentially controls whether you can access a page or you cannot access a page at ring 3. So the green pages will be mapped with this bit set, meaning that the translation will go through and says, okay, everything is good. But if you try to access an address somewhere over here above the 2nd gigabyte, this bit will not be set. And then there will be I forget exactly which fault will be executed. Maybe it will be a page fault, or maybe it will be a protection violation. And this is how this mechanism is enforced. But we're going to cover specifically what it means to run it at ring 0, ring 3. We will cover segmentation, how it's all mapped and created, and then we will cover how those page tables are also constructed and how this bit is set. But again, like, I appreciate your curiosity and the fact that you know and have this feeling that, yes, so look, that something is weird, right? So how come, why this direct access is blocked? It's blocked at the level of the page table, those entries. So either at the page table directory or at the level of a page table, either this or this bit will not be set, right, for the kernel. Got it?
Yeah, got it.
But again, we will get to these details, and I appreciate again that you jumping ahead. Any other questions? How does heap find memory, empty memory it can use? That's a great question. There are multiple organizations of memory allocators, and I will try to. In the past, I didn't have time to teach a lecture on memory allocators, but I will try this year. But roughly speaking, it's a collection of metadata. So roughly speaking, you say, look, I can do something as simple as a linked list, right? And say, look, this is my first empty element. And there will be a pointer to the next empty element. Again, next empty element, right? And when you say, look, I will pick one element and return it to user as a result of malloc, right? You will just remove it from the list, right? And you say, look, but what about different sizes? And you say, I will have a list for each size. For size, for example, 16, 32 bytes, 64 bytes, and then you will round up and return the element from that list. That's one realistic organization of a memory allocator. Does this help?
It does waste space, right? Like if we are, I'm just thinking, like, so if it's 16 and 32 bit, like, and like if the program is just like, if I'm just asking them allocking only for like some 8 bytes, it will give me a 16 byte chunk.
Yeah, it will. Yeah, there is a wastage. So if you allocate 17, you will it will be rounded to 32, and you will waste like 15 bytes. That's a trade-off which people do to make sure that malloc is faster. If you're on a specific workload in which you constantly allocate 17, you might figure out a different memory allocator. Although I don't think anyone does it at this point because memory is relatively cheap. But again, if you're talking about billions of objects or trillions, then you might think about it. Okay, good. Let's keep going. So one question. So where do these areas come from? Yeah, like a little bit obscure question. But if I ask you these, and these, where do they come from? Oh, like what I mean is that you're not going to just create empty pages, right? So for some of those sections, you will say, look, I will load some meaningful data into them, right? And what I meant to say here is that those two guys are created by the compiler and the linker, because when you compile a new program, that will be your code of your program, right? Compiled from multiple object files. And of course, same for the data section, because there will be variables from libraries and again, multiple object files, which come from different source files, right, which will be merged together here. And these two will be allocated by the operating system. So they will be originally empty, right? So your malloc library will at some point trigger as BRK, or on the very first system call, most like on the very first malloc allocation, and then operating system will allocate a page, for example, if SBRK says, give me, for example, 1 page. And the stack is configured when most likely it will be configured by the operating system, right? Unless it's a language runtime, something like Java, in which, in this case, the runtime will take care of it. But when the process is loaded, essentially, before even loading the process, the operating system will allocate a page for the stack, for example. So the process can, the main can start executing and will, because you pass arguments to the main on the stack, right? Okay, that's what I meant to say here. Okay, so let's quickly just look at this example of a program here. It's a very simple C thing, which says, okay, I have main function. I will have 2 integer variables, a and b, which are 5 and 6. It's initialized to 5 and 6. And what main does, it just returns the sum of a plus b, right? And I will use this GCC compiler saying, even if I'm on 64-bit machine, please compile 32-bit code. Do not compile position-independent code because it will complicate our analysis. And please just use this one simple hello init C file, right? And this example is there online, like you can access it from the class web page. And if you use an object dump tool, which is a tool which allows you to look inside the program and see what's in there, passing 2 arguments here. So S means please show all the sections of the program, and D means please disassemble the text section. It will show you this output, right? One additional wrinkle here is that when I was creating the slide, I was using the AT&T syntax, right? So essentially an instruction which uses AT&T syntax moves from ESP into EBP, right? On Intel, it would look something like this. EBP gets the value of ESP, right? So that's how Intel syntax writes it, and this is how AT&T syntax writes it. But I will always clarify which way it goes, right? So remember calling conventions. That's where you enter the function, right? So that's your disassembly of the main function. You maintain the stack frame, so you push the old EBP on a stack, right? And then immediately initialize EBP to the current value of ESP, marking the beginning of the new frame, right? So we covered that last time. And what I meant to say here is that in this text section, which is here, right? If you carefully look at it, right? You will understand that those bytes of those instructions, so those are actual opcodes, which CPU can understand and read from memory. You remember this fetch, decode, execute loop, right? So you will find them here. So this one byte instruction, which pushes EBP on a stack, is 5.5, opcode 5.5. And it's right here. The next instruction, and this is a 2-byte instruction, right? So I told you that instructions are of variable size on x86. So it's a little bit inconvenient, but still okay, whatever. They decided that it's creates more compact programs, right? So it has those bytes 8, 9, and EB, right? And you will find them here, 8, 9, and EB, right? So I'm just saying that it's really like disassembly. It really takes the text section and shows you in a human readable form, right? If it can, right? And of course, sure, it's familiar things. Maintain the stack frame, as I just said. The next instruction, remember, allocate space for local variables, because remember, we had 2 variables, A and B, right? And since we're doing the stack alignment, GCC does it, right? So we allocate, instead of just allocating 8 byte, we will allocate 16 bytes on a stack by subtracting 16 bytes from the ESP pointer, right? And this constant, which is 16, hex 16, right? It's right here, right? So if you carefully look at the code, you understand, okay, look, I got it. So this is a 3-byte instruction, and the immediate value of this instruction, which it uses, is x10, right? Or 16 decimal. Same here, right? So I highlighted here. So same here. So you initialize those 2 guys to A and A. You initialize A, which is allocated on a stack to 5, and B, which is also allocated on a stack to 6, right? And if you carefully look at it, you will see the same values. Like this is immediate values inside the instruction. So this is a long instruction. So it takes 1, 2, 3, 4, 5, 6, 7 bytes. It just unbelievably long, right? 7-byte instruction, right? So who knew these instructions even exist, but they do on Intel, right? Some of them are 1 byte, some of them are 7, right? So 5 and 6. And if you're carefully looking, because okay, those constants which encode -8 in hex, right? If you carefully look at the encoding, right? So you know that XFF is -1. So obviously FC is -4 if you just keep counting, right? And if you don't remember the representation, right? So -2 will be XFE, -3 FX ABCD D, and -4 will be FC. So this is -4, this is -3, this is -2, this is -1, right? So you will find those guys immediate again. Like you say, look, I want to it's EBP -4, right? Because you go up the stack, right? Sorry, down, because EBP just sits above those variables, right? ESP would be ESP plus something, right? Okay, got it. And like you can see those constants inside the instructions, right? So this is where you load this. I mean, like if you want to see the assembly again, right? This is, and again, I forgot if we probably ran out of time last time to look at the examples when we were looking at calling conventions, right? Or the point which I'm trying to do here, right? I can run it live, this specific example, and then use opt dump, right? Just created a slide out of it. But really, if you take this code, compile it, you will see the same. And maybe I will do that next time as well for you with some different examples, but still. Right, the point is that everything is real. So this is exactly how your compiler, GCC compiler on those machines will compile the code, right? Here we, again, since we didn't enable at least even optimization level 0, everything is very like verbose here. So first we initialize something on a stack, not immediately putting it in registers, and then we move these things from the stack into a register so we can perform the computation on them, right? The next instruction essentially adds A plus B. So leaving the end result in the EMX, right? Remember, it's AT&T syntax. And at this point, we can invoke this leave instruction, essentially just popping the EBP, right? Restoring the old value of the EBP and returning and essentially invoking the red instruction. And those two guys are 1 byte instruction, right? Instructions. And if I ask you what these two guys are, right? Some random instruction after the red, because you know that if you start executing main, you will never actually reach those instructions, right? But those ones which essentially set the EX or AX to 0 twice for whatever reason, right? Those are used for code alignment, right? And this NOP instruction. And compiler can generate different instructions for code alignment. And the reason for this is essentially coming from, again, this assembly optimization manual written by the same guy, Agner Fopp, who says, okay, like most microprocessors fetch code in a line 16-byte or 32-byte blocks, meaning that the processor will read this block from memory or from the cache, right? And it means that if you suddenly, your subroutine, and if an important subroutine entry or jump label, meaning when you jump to the label, happens to be near the end of this 16-byte block, somewhere over here, for example, right? Maybe that's the beginning of your main function, right? That means that the processor will have to, might execute like 1 or 2 instructions, but then it will have to read this block again, which might introduce a tiny delay, right? That's why it makes sense to put the beginning of main here, and then the processor will utilize all this block, right? And that's essentially the result for this alignment, right? Whether it's, again, it only matters when you want to do the cycle accurate optimizations, but I just wanted to explain you that this is what compilers are doing. They're designed to do that, right? Okay, cool. So let me again quickly stop here. Are there any questions about this opt dump or alignment slide? All good? Okay, let's keep going. So, okay, and now the question is, okay, what needs to be done to load the program from memory, right? Essentially, it's kind of relatively easy. So you say, look, I will allocate, if I'm an operating system designer, imagine I have a file system, and so I can access the file of the program, right? Something like bin.wc, right? So that sits on disk. There will be some format here. Let's imagine it's ELF. it will have a header here, and then like a data section and a code section, and maybe some other sections like information about BSS, but maybe some information about debug symbols, stuff like that, right? As an operating system designer, I really like just allocate a couple of pages of memory, read the data section by like looking first at the header, saying, okay, the data section starts at a specific position in the file, and then just load this guy in memory, right? And they say, oh, sorry, I missed it. It's actually code, not data, but vice versa, right? When you will be like, you will load it here. And if you're doing the code, again, you will allocate the pages, load them here. Then you say, look, I will actually don't do anything with a heap, right? Because the program will start running, will perform its first call to malloc. Malloc itself will see that the those linked lists are empty and will allocate the space for the heap. But the operating system, will allocate the stack. And at this point, you can just essentially create on the stack. If you're passing some arguments, remember this argv array, you just initialize it here on the stack. And at this point, you can jump to main, and the main will essentially look up at the argv array on the stack and will start running, right? So kind of so far so good, like reasonably simple. I mean, at a high level, in layman's terms, you can actually say, okay, look, I can write it. Just give me this template. I will write it overnight. It will be running by morning, right? Okay, right? And there is a couple of issues here. And one issue is that we actually develop programs or compile them or link them to multiple files, right? And there is an essentially modularity, right? So there are multiple reasons, and we'll go over them in a second, right? But roughly speaking, it's easier to just maintain the code in such a manner that it's split in multiple source files, right? And then you can compile individual files and just link them together later into one executable, right? And for that, you will be using some kind of a build system which allows you to compile all the source files into object files, right? And what the object files are, there are again L files with data and text section, right? And the linker will just go through all of them and essentially just merge them in together into a single executable or shared library, right? So this is example of a boot block target from the x86 makefile, and I know that after the homework, you now know everything about makefile, so you're good to go, right? So what happens here is that we're taking two files, bootasm.s, assembly file, and a C file, bootmain.c. We compile them individually. So this is bootmain.c, bootasm.s. Each of this will produce an object file, .o, right? And then we say, look, use the linker and use those object files, which we got from here and from here, right? And please compile something what is a single object file out of these two, essentially kind of merging them together, right? And do some specific tricks on it. Like, please make sure that the program, if loaded at this magic address 7C00, this is where the boot loader will load this boot block, make sure that the code will run. So the global variables, everything will be linked in such a manner that the program is correct, right? And I will explain what it means in a second. And please use the start label as the entry point, right? So far so good. Again, like we kind of got it. We have this intuition that we compile programs from multiple files. And today is essentially the main subject of our lecture is essentially to make sure that we understand how this linking and loading works, right? Okay, any questions up until now? All good? Okay, linking essentially is relatively simple, right? So you're combining multiple code modules into a single executable, right? Or a shared library, or static library, if you want, right? And then you use standard libraries. That's dumb. Okay, whatever. And loading is a little bit trickier, right? It's essentially the act of like taking this executable, placing it in memory, and making sure that the code is prepared or relocated to run at this specific address at which operating system puts it, right? And sometimes some operating system uses use linking and load and relocation steadily. Like essentially the programs are ready to run at a specific address, like at address 0, for example. This is how x86 does it. But some operating systems like Linux, they say, look, I will take it from the disk and it's linked to run at 0, but really I will place it at address, some different address, right? And then there is an act of relocation to essentially to make sure that all the references to global variables point to proper addresses, right? And essentially, I will explain it in a sec, right? Okay, let's take a look at this high-level picture, which is a little bit naive, I guess, but just again. So the C compiler or some other language compiler, we even like took a bunch of those files, right, and produced a bunch of object files, right? So each of these object files, today it's an ELF, although it can be a different format, right? It, as I was saying, it has a header, which describes which section it has, like where's the data inside the file, where is the code inside the file, right? But all of them are more or less similar, right? There are some also shared libraries, and I will explain what these are, but you kind of can guess what I'm getting. It's also ELF with some data section and some code section as well. There will be, they call them normal libraries, but those guys are really like just static libraries, right? And static libraries are essentially bundles of object files kind of placed in a special archive with an R tool, essentially just an archive, which is full of these object files. So, and each object file itself is an ELF, right? And the linker essentially can take some command line arguments, can take some linker control scripts, right? And this is what x86 is doing. And essentially we'll take all of these together and we'll produce an executable file, right? Or maybe a shared library. And it will produce a symbol, debug symbol files. And sometimes this debug information, today it's typically just merged inside and placed in a different section here, right? So again, kind of at a high level, it's clear, right? And we got what the inputs are and what the outputs like. So outputs can be a file which can be executed directly at a specific address, can be a file which can be executed, but also relocated, meaning that it can be shifted in memory, so moved. So when the operating system will load it, there is enough information to move the file in memory to a different address, right? It can be a library, because on the output here, you don't have to like produce an executable. You can produce a shared library or again, a static library, right? So, but linking is essentially just merges multiple object files together, right? And the reason for this merging is that when we typically write code, again, to keep it modular, we will say, look, this object file has a, let's assume it's a function A or a variable A. So it's a symbol which has which name L, which has name A. It's implemented inside this object file. And it calls or accesses B, C, and D. And those B, C, and D are nowhere around. So that's why we have to really suck in other object files to find them, right? So here, B, for example, this object file implements B, but is missing C and E, right? In some of these libraries, like which operating system can locate, or like linker can locate, right? Provide C and D, for example, and maybe E and F, right? And essentially when we use the linker, it will say, look, I found A here, and I will put it here, kind of merging those data and code sections together, right? I found B here, so I will place it, merge it here as well. I found C and D here, so I will put them here, and I found E here, right? So now when A calls B and C and D, essentially A calls B, now it knows that B is here, so actually we can perform a call instruction with a specific address, right? Same for C and D, right? So all these symbols which used to be unknown, now resolved, right? And I will explain in a second what it means, right? But essentially you kind of, I hope you got the point here. So it's essentially merging multiple object files together, trying to find symbols which are provided by the object file and the symbols which are missing. And those missing symbols have to be resolved, found in different libraries or in other object files, right? And if the symbol is missing, most likely the linker will return an error, and like in most cases, you would say, okay, look, I'm not going to run this program. Also, you can, because maybe most parts of this program actually will run there, and you will never reach, there is no execution path which reaches this unresolved symbol. So you technically can change the linker to say, look, whatever, forget. If I don't, I'm pretty sure it takes an argument. If I don't see a symbol, forget about it, just run it like that. Let's hope for the better, right? So again, let me stop here, take any questions. So is it too easy? Like everyone knows how it works? We'll get a little bit more involved, don't you worry, in a second. Okay, I already asked this question. So why are we linking programs? Who can tell me? Anyone knows the answer for why we link? Why not to do, why dynamic linking? Hold on, like we don't even know what dynamic or static, or let's say just linking in general. Okay, I have those childish questions, but I wanted to think a little bit about it. So I mentioned modularity, right? So program can be written as a collection of modules, meaning like C files, right? We can build libraries of common functions. So essentially, first of all, there are two things here. So first of all, if you change one source file, you can recompile just this source file as long as your build system, like a make file, keeps track of dependencies and said, look, other C files didn't change, so you don't really have to recompile them, right? And then you just relink the executable. So as actually, it's a good strategy. You save a lot on compilation. Unfortunately, linking itself is kind of a bottleneck today because it takes quite a bit of time to even link. Well, the compilation is much more involved, but even linking itself can take time in projects like Linux kernel. You can also use argument for space and memory efficiency, meaning that if you share common code across executable files, right, you can put a library on like of this common routines, right, on somewhere on disk, right, and every time you load a program, this library will be loaded. So this is your main, and printf, for example, is here, right? And you load this library in the address space of a program, or even map maybe. So maybe the same physical pages which contain the same kind of printf implementation will be allocated once in physical memory, right? And then mapped multiple times in like process 1 and process 2, which will have a totally different main here, right? And as long as you patch correctly those invocations, right, everything will be just working together in these two processes, right? So, but you got the point. So you can save space on disk and you can save space in memory, right? Again, it's much less pressing today because we have giant disks and huge memories, right? And actually DLL HAL is a much bigger program. You say, look, I rather like, I will put it in the entire container just so the like all the libraries are like for sure there, and like no other libraries are visible, so the linker will not do anything funny, and like my stuff will run, right? So that's essentially, this is where we are today. But back in the days, disks were expensive, and probably my first hard drive was smaller than the memory of this machine. Not maybe, but for sure, right? So stuff changes and those equations change, but we still get stuck with this linking. But maybe you can roll out like a special, either in industry or in academia, you say, look, I understand those overheads, so I will optimize them, and like they will disappear. Okay, so linking is a two-pass process, right? So first you scan the input files and you identify boundaries of each segment, like data sections and text. You collect defined and undefined symbols, right? Because you have to keep track of what's undefined and what's defined and where, right? Like determine locations and sizes of those data and text sections, right? And then you merge them together and you adjust the addresses to make sure that if you access the variable A and actually you moved it in memory because, maybe it was your data section, but now you merge it with a different data section, and now the address of A is different. So you have to patch the code to make sure that you access correct address. Let me illustrate it with a couple of diagrams here. So here you have, like, imagine this is like kind of like, let's just go to the next slide directly. So you have this object file A, right? And it has a text section and a data section and its own BSS, right? You have B, which also has text and data and its own BSS. It's like It's kind of shaded here because it's not kept on this, but you know that we will allocate BSS, right, and C. And so what linking and loading is doing, you say, look, I will take text section of A, we'll put it here, text section of B, we'll put it in a single continuous location, not location, but single continuous region of memory, right? So you will take text of C, you kind of merge them together, and maybe you will, like, if you like relinking into a shared library, you will just put it back on disk as another, like an ELF file which contains the shared library. But if you're loading the process in memory, you're going to merge those sections, right? And the same with data. So you will have a data section. This is A code, B code, C code, A data, B data section, C data section, ABSS, BBSS, and CBSS, right? And look, if in your code you said, look, I was accessing variable in my data section, which was maybe at address x55, and maybe for A it didn't move, so it still stays at A55, although most likely it moved because we grew a little bit the text section, right? So, and now this variable is at some different address, maybe it's like 2057, for example, right? So if you were doing a move instruction here, which was accessing this variable var, right? So you have to patch actually this immediate value. Remember, I showed, like, I mean, I didn't really show you example of how the data section gets accessed, but I will show in a second. But you saw those like immediate values inside the functions, inside the instructions. We said, okay, look, I am accessing -8 bytes on the stack, right? So now if you have this move, so better, this value of var better has to be pointing exactly here, right? Not at x55, right? And this is essentially the process of relocating the linking and relocating the binary. Relocating means just moving up and down in memory, but linking means like essentially merging those sections and patching those addresses, right? Right? Okay, let me ask you a question. So what needs to be done to merge multiple sections or move code in memory? Who can tell me? Like, we know enough about how we know the shape of the code, right? So there are instructions, right? There are something like move for ESP in, like, you want me to use Intel into EBP, for example, right? So let me ask, relative addresses need to be changed. Hold on. Relative addresses actually don't have to be changed, right? Because they're relative. You say, if you can say, look, I'm making a function call and I'm calling 3 bytes from here down from here. So maybe I'm calling label A, and label A is this relative address is actually +3, for example. Then this distance doesn't have to change, right? So I would say absolute addresses need to be changed. So in this instruction, nothing needs to be changed because it uses registers. If you do something like push on a stack, again, even push EAX on a stack, right? It's just fine because if your value of ESP is correct, you will just push on the stack. ESP is already set up by the operating system. So this you don't have to change. But if you do something like move and you're using address of a global variable, this you will have to change, right? Because obviously say, look, my data section is moving in memory, so I have to patch all these addresses. And if you call the functions which were undefined and you were not able to generate a relative address. So again, calling something like label B, and label B is somewhere in memory, right? Then you will have to change this label B here, right? So more or less, we kind of got the point. So some instructions don't have to be changed, but the addresses of global variables and functions which were not known to be relative to your current code, because when you're merging 2 different pieces, when the compiler generated this first invocation to begin with, it didn't even know where B will be, right? So like, bear with me for a sec, right? I will provide a little bit more examples, right? So this process of like moving the binary essentially and merging and moving are very similar, because moving is kind of like you already merged everything, but you just have to patch those addresses because you move the binary up and down in memory, for example. Let's consider this very simple example, trivial, right? So A gets assigned to B, right? And imagine those are two variables like in data section because they're globals, right? So in this example, again, we're using AT&T syntax. So instead of writing like move A into, hold on, move AT&T, move into EAX from an address pointed by A. This is Intel syntax, right? In AT&T, the same thing is written this way. So use A address and move into EAX, right? And then from EAX, move back into B, right? So the compiler will generate the following code, right? In this example, imagine A is defined and is in the same file at this, in the data section at this location, 1, 2, 3, 4, right? But B is imported. So when I say imported, it was declared something like extern int B, right? And the compiler knows that it's an integer. It knows the type, so it can generate the code to process B, but it doesn't know where B is, right? Because it's extern. It means that it will be provided in the other object file, and the linker will essentially, at that point, will resolve the location, right? So the code which gets generated is following. So again, a 1-byte opcode, right? So it's essentially encoding this move instruction, which moves from A into EAX. There will be an address, 1, 2, 3, 4. And you will see it in this weird manner just because the x86 is a little endian system, right? And so essentially, your 32-bit integer will be placed, the highest address will be placed at the further away position, right? So it's this way, right? So those, the high addresses are 0, 0, because this is address 0, 0, 0, 0, 1, 2, 3, 4. Right, and the highest address will be further away from your opcode, right? So let's just flash back to this big and little endian systems, right? Which, I mean, I don't know if you ever paid attention to endianness, but this is how it is on x86, right? Okay, cool. So we know the address, so the compiler will generate this address for now, right? But for B is important, so there is no even good location for, like, no good address where B can be. yeah, me too. For like compiler doesn't, it can guess some address, but it doesn't make sense. So it just places zeros here, saying that B will be found later. And there's a special section in the L file which keep tracks saying, okay, I know that A is defined and it's used by this instruction. So anytime you use A, there might be another use somewhere over here. You will, and if the data section changes, you have to go ahead and patch those addresses because otherwise the code will not run. And by the way, there is another thing about B, and B is just simply undefined. And so it's used here, but we haven't found it. So, and maybe it was used here as well. So it will keep track of those places and will say, look, the moment you find B, go ahead and put those addresses there, right? So at a high level, you kind of get the idea, but this is the code which gets generated. So, okay, imagine in a final binary, we like merged everything together. We said we're linking the program to run it. Let's imagine that this magical address, which was, we've seen previously, 7C00, maybe we're linking a boot block, right? We say, look, okay, sure. Our data section is moved by this number, x10000, right? So, which means that this address, you have to add this 10000, right, or x10,000, right? Just because, look, you say, look, it's no longer at 1, 2, 3, 4, it's plus this address, right? This is where we moved it, right? So essentially from, it used to be here at 1, 2, 3, 4, but now we added this x10000, right? So it's somewhere here in memory. So if you had a move instruction which uses it, right? So this address inside the immediate value inside the move instruction should be pointing to this new address, right? Okay, cool. And at this point, we say, look, and this B is actually found now at this address, 9812. So now instead of like having those zeros here, we will replace them with 129A, again, accounting for little endianness, right? And at this point, like, it's all correct, right? So this address points to this location in memory where the data section is and where this A variable is allocated, right? And this location is also pointing to somewhere in the data section where the space for B is allocated, right? And those two data sections, like split is incorrect. So this data section came from like one object file, and this part of the data section came from another object file, right? So this is like when the linker was merging them, it was merging the data sections and was merging the code sections and was patching all the instructions which access variables which are in a global data section, right? So, okay, let me stop here for a second, take some questions. Is this example clear? Sorry, who will fill in the address of B by linker? It will be linker. Compiler takes your C file and essentially compiles it into an obj file, producing a data section and a code section and BSS if needed, right? Code. And if you take another C file, right, this is 1 and this is 2, compiler again just simply will produce an object file, and this will be placed in a container which is called elf, right? You probably have heard those names, elf, right? It's just a container to keep this data sections, right? Nothing special. We'll have a homework about it, so you will learn all about it. This one will also have a data section and a code section. And technically speaking, I mean, some compilers have linkers built in, and it's okay, right? But it's logically, it's a separate process, which is separate part of compilation, so linking. So you will have two object files, and the linker will merge these two data sections into a single data section, right? And will merge two code sections into a single code section, right? And maybe relocate the binary to start running at 7C00 as I was using in my example, right? And at this point, this thing can be placed on disk and been simply loaded in memory at 7C00, and everything will start running this data and code section here, right? Got it? Okay, any other questions? Let's go through some other examples since we're on it, right? They're a little bit more realistic example. So here we have two source files. One is called m.c, another is called a.c. This guy has main, and main has one global variable, which is hello world, right? It's global because we declared it to a static keyword, and it calls a function. And the a function itself is actually an extern function, right? So it says we know the type. And why do we need this type actually? So who can tell me? Why do we need this external invocation? So what will go wrong if this line is not here? Who can tell me? Function never defined. So yeah, undefined function. And what's the real problem with undefined function? Since it's still not defined, it's just we know the signature of a function, right? So we don't really know what the body of this function is doing, right? Okay, maybe you never thought about it, but let me show you. Like right here, the compiler will generate a call instruction, right? And it can say, look, I don't know where the address of A is, so I will put just some zeros here, for example, right? But what's the problem? Like, why can't you just leave it like that and just move forward, right? Because who cares? We don't know the address. Call instruction is here, so supposedly it should run at this point. So what will crash at runtime if you just leave it like that? We are actually breaking the calling convention, right? Because this function A, it will be defined somewhere, and it expects to have one argument passed on the stack, right? Because it says, look, it's char here, right? Let me just quickly erase the link on the slide. So we'll have this call, right? And A will be accessing this argument with like relative to EBP register, right? That's why we covered the calling conventions, right? So in order to correctly generate the call site invocation, we need to put a push instruction here. which takes the address of this like string, right, and pushes it on the stack, because this is the 32-bit Meta-cle calling convention, which we covered last time, right? So if you have one argument, you push it on a stack and then invoke the function, right? That's what is missing. So, and this extern declaration essentially provides us the signature of a function, telling us this is the return value and this is one argument function, right? And that's why the compiler can generate this sequence even without knowing what the function is doing for real. And this is typically when you include a file, right, in C, when you do include something, right? Includes are just like a bunch of those signatures. Essentially, you know what the data structures are and you know what the function signatures are, so you can essentially generate code to access fields of individual structures, right? You know the offsets and you know how to generate cosides for those functions as well, right? Got it? Yeah, exactly. So we need is exactly. So okay, cool. So in our example, A is undefined in this first file, right? So it's extern, and essentially A is defined in another C file, right? That's the definition of A, right? So it takes one argument and it uses two system functions. One is a stringlen, strlen, which takes the size of the string, and what is using here is the write function, which uses the standard output descriptor one, right? Essentially passing string, which is passed as an argument here, and here it's the size of a buffer. So it's strlen will provide you this size, right? So you got the point. Okay, now let's take a look what code gets generated by the compiler, right? Okay, this is again kind of opt dump of that m.o, right? So we took m.c and compiled it into m.o, right? And so what happens here is that the compiler said, okay, look, I generated two sections. One is a text section, right? So its size is only 16 bytes, x 10, right? And the data section is also like size is only 16 bytes. It just so happens in this example, right? And I compiled right now, I linked the code, or I compiled the code for the text section to start at 0, and the data section will start at byte 16, right above the text section, right? Okay, cool, that makes sense. And the code starts at 0, so that's why you say at address 0, I will find main function. We just mangle the label a little bit, like adding this underscore, right? And again, after that, all familiar code essentially, right? So you maintain the stack frame as I was teaching you before, right? And here, since this is this push argument of a string on a stack, right? You know where the string is. You know that it's in the data section, right? So the compiler knows it's exactly at byte 16. That's why 16 is used, right? But remember that it's a global variable. So the compiler will add a specific entry, which is visualized here, saying that, okay, by the way, here, this instruction is using the something from a data section, and later this address, if the binary is relocated in memory, this address has to be changed, right? It's physically it's put in a different section inside the L file, this information. It's just that opt-dump can print it out right underneath, so you like it's easier for you as a human to read, right? Okay, that's cool. And you say, look, that's essentially we're doing this invocation. So we're passing a string, right? We know where the string is. It's our variable. It's in our global section. A is not known, however, right? The compiler generates this code essentially saying that I will be using some negative address here. So kind of like looping around, saying if worse to worse, I think this instruction gets executed, it will just jump relative to the end of this instruction and will be maybe executing it over and over again, right? And sure, and also there is an information saying that, okay, look, and by the way, we're looking for symbol A. It's undefined, right? So it's nowhere around. We don't know what A is. So please, when you link the final binary, so patch this address, make sure that it will be pointing to A, right? So far, so good. So we go to the other opt file, right? So here we, again, at a high level, we say, look, this is an implementation of A, which calls these two functions, stringlen and write, right? So again, we kind of know what the deal will be, right? Again, two sections. So one is a text section, which is 28 bytes now, 1C in hex, right? And one is a data section. There are no global variables, so it's empty. So it's actually size is 0, right? But it starts right above on 1C, right? So this is how it's encoded, right? Then again, since we're talking about those invocations, right? So we are first invoking a string len function. So we will have to push the argument, right? So right now the argument was moved from the stack into the register. Hold on. So what is that? Yeah, EBX, right? So I somehow thought that we're using EAX register here, pardon. And then call, again, since we don't know where string length is part of the system libraries, right? So it's not part of those two C files, right? So it's not part of your program, it's somewhere else, right? So we say compiler again generates this magical addresses saying we don't really know, negative. And for the second call, they're called to the write function. So here we're pushing the file descriptor number 1, we're pushing the string from the EBX, which is here, right? And we're pushing the size, which is returned by string len in the EAX register. Remember, integers are returned in the EAX register. This is why it's so useful to know the calling convention. Suddenly you can read the assembly, right? It's a very good skill. It's unoptimized, but it's still like, even if we enable optimizations, actually this one is reasonably optimized. I can't see like a lot of goofiness here, right? But you can suddenly understand what the code is doing. Just because you understand the calling convention, you know that strlen returns something in the EAX register, and you know that like to push the arguments, you have to pass the arguments, you have to push them on a stack. So this is kind of brilliant, right, at this point. Okay, cool. But our topic today is linking, but there is a deep connection, right? So that's why I was explaining, that's why I gave you a lecture on assembly, and that's why I gave you a lecture on calling convention. So now everything, there are no black boxes, everything is kind of open, right? So you can look through and understand what's going on. Okay, so this is two call side invocations, one for string len, takes 1 argument, once for write, takes 3 arguments, right? And again, as I was saying, that like it will record the fact that string len is missing and write is missing right now, right? So far so good, right? So are there any questions about it? If we do not include the extern of a function A, will we be able to push the accurate return address? Will we be able to push the accurate return address of a function on stack? No, return address, remember, when we call a function, what gets pushed on a stack is this, right? Even if you don't have A, so for example, this is the call to A, and I will erase everything on this slide, right? This address, this D will get pushed on the stack, right? Because you're saying, I will be calling A. Remember, you're pushing the return address, but you're jumping to the label. So to jump, you need the address of A, but to return, you already know this D, right? Got it?
One question. Can you go to the previous slide, like where you're explaining why the extern is required?
Hold on, actually, can you hear me right now, right? I didn't notice, but I probably muted the other mic. So can you hear me?
Yeah, I can hear you.
Okay, cool. So can you ask the question again? I apologize.
Yeah, so in the like in the slide where you explain why we need to declare the function signature before calling.
Yeah.
So there in A string, right? You were saying like we need to know the arguments to push it on the stack. Like there we can
right. You need to know the address of A. So this address, which is not the A, it's the address of string.
Yeah. Okay, but that string is in stack, right? It's already defined previously in the previous statement.
It's not on a stack. The string is in the data section. So this is the data section, which is 16 bytes, and the string is exactly those 16 bytes. Hello world. So you're pushing the address. So look, your data section will be in memory, right? And there will be like literally hello and so on, right? It will be some address A, right? And this instruction says, look, I have my ESP register pointing to where my stack is, but I will take the address of string. I know that this is A, and I will push it on a stack A, right? This address A, which is in this case, it's exactly 0x10, right? So this 0x10 will be pushed on a stack, right? Do you think you get what I'm saying?
No, do we need to know that it's a string, or do we know to know the string?
We don't need to know that it's a string. So because we're passing a pointer. If it would be like a data structure and we're passing it not by reference, but by value, then we would like push parts of this data structure like on the stack, because it would occupy multiple bytes, right? But here we know that we only need to know the type to implement a call, right? So, and pointers to any type are the same kind of size, right? 4 bytes in C, right? So that's why it's easy, right? You just always push, right?
Yeah.
You got this?
No,
Yeah,
my
go ahead.
question is like the reason we need to define the functions. You were saying like we need to know the function signature in order to push those variables into the stack.
Right.
That's yeah. So
Imagine you have a function called. Imagine you have a function B, which takes 2 strings, the char
yeah.
A
So
and char B.
my question is, why can't we just use instead of the function definition, in the function call we pass the arguments, right? So why can't we just blindly push them onto the stack and call it?
No, but wait, you need to know how many. You do 1 push if it's 1 argument, or you have to push 2 arguments, right?
That is already defined, right? So the type of it is already kind of defined, right?
No, but for that you need to know this bit of information. You need to know that this is a function which takes 2 arguments, right? That's why you will put something like extern, right?
I think he's saying that you could trust
Yeah,
the call
exactly.
signature. You could trust that the call signature is the actual function signature.
Yeah, exactly. That's what I meant.
I don't get it. So how can you guess how many arguments the function will take?
No, in the previous, can go to the previous slide once. So yeah, here we know that the string, okay, the string is a char. We can actually detect from the previous line number 4 that.
You're saying you can. Wait, hold on. You're saying that if the developer says a string and then some foo, right? You say from this line, you can essentially guess what the type is, right?
Yeah, exactly. Like
Okay,
string is a.
But here, for example, here we don't know the return type, right?
Yeah. But that's still
yeah, you can do this tricks, and so the technically speaking, yes. So you can probably generate the call side from this. The C compiler will just type check saying that, okay, are you sure that you're invoking the function correctly? Because if you don't know the type, it will not be able to type check. But I got your point. Yeah, you're right. So if you want to play tricks, and I lost my pen. If you want to play tricks, let me just quickly find it. And say that, okay, I don't care about type checking, then you should, yeah, you can do this trick, right? Absolutely. But you will never be able to correct programs in which programmers will like implement incorrect function invocations, right?
Yeah, but that I agree. That I agree. I was just thinking, I was just looking at what if this can be done.
Yeah, and you don't really know what gets returned either, right? So yeah, it's for type checking as well. Okay, so 720. Okay, let's stop here and we'll come back and look at what happens to those 2 object files next time, just so I don't keep you over time. And essentially, we'll take a look at how this gets merged together and how the final executable is produced, right? So let's stop here and we'll see you then on Wednesday. Thank you.